The Earth has three main layers: two parts of the core, the dense, hot inner core, and the molten outer core. Then comes the mantle. And then follows the thin crust, the surface that supports life as we know it. At least, that's what we thought, because now scientists found a new mysterious layer located deep within the solid inner core. Earth's inner core is approximately 2/3 the size of the Moon. And made of nickel and solid iron, it's burning hot. The temperature at the center of our planet is the same as at the surface of the Sun. The outer core can reach almost 10,000 degrees Fahrenheit. It's difficult to explore it because we can't go there, and it's like looking through a really dirty window of 3,200 miles of molten metal and rocks. But we can rely on laboratory experiments on heated pressurized rocks, signals from seismic waves, and computer models. When an earthquake hits, it sends out seismic shock waves. Those waves travel through layers at a different speed, depending on the direction they go and the material they move through. In the new study, a team of scientists set a data set of 100,000 deep earthquakes. Some of them went over 60 miles below the surface. When an earthquake happens on one side of our planet, scientists track its waves all along to the other side. Waves change when they come to the other side, so scientists try to understand the materials these waves have passed through. They found a new layer in the core of our planet thanks to earthquakes. Normally, shock waves travel along the equator, but down below, they digress and go into different directions, about 60 degrees to the side. When waves pass through the inner core going from north to south, they will travel more quickly than waves going through the core parallel to the equator. It's important to understand the core because it creates our magnetic field, which in turn protects the planet from things like solar winds that are charged particles coming from the sun. In the 1960s, we discovered the Earth pulsates every 26 seconds. It's like clockwork, a giant heartbeat. The ground is slightly shaking, but we mostly don't feel it. Researchers can still track it. Some of them think the continental shelf comes as a huge wave break under the oceans. For example, the highest part of the North American continent falls off into a deep abyssal plain. One theory says waves hit this spot, producing regular pulses. It's like having all kinds of drums. You hit them with your hands and accidentally slam that one spot that produces the right harmonic bang to rattle our entire planet. If this theory is true, we're lucky there are no more spots like this that can shake the Earth. Other scientists believe the pulsation happens because there's a volcano near the critical spot, the island of Sao Tome in the Bight of Boni. You're walking, running, and jumping, but when you stop, it always feels like you're standing still. In reality, you're moving even when you're perfectly still because our planet is always on the move. Depending on where you're at, you could be spinning through the universe at more than 1,000 miles per hour. If you're on the equator, you'll move the fastest. Let's say you have a basketball spinning on your finger. Check the ball's equator. A random point on it has farther to go in just one spin than any point near your finger. That means the point on the equator is moving more quickly. The Earth is a planet that recycles all the time. The ground we're walking on is recycled. Our planet's rock cycle turns rocks of one type into another. That's a cycle that goes on and on. The depths of our planet are filled with magma. As magma is going out onto the surface, it hardens into rock. Tectonic processes like volcanic activity, earthquakes, mountain building, and all of the other processes that shape the surface of our planet bring that rock to the Earth's surface. When the rock is on the surface, erosion shapes it and shaves its bits off. Those small particles then get deposited. All the pressure coming from above compacts the particles into sedimentary rocks, like, for example, sandstone. Sedimentary rocks can also end up deeper and deeper under the Earth's surface. Since there's a lot of heat and pressure, they get cooked into metamorphic rocks. They can go back to the surface once again, or even end up being re-eroded. Sometimes the crust plates are pushing one under another, and this way, rocks can transform into magma once again. We've explored only 5% of the ocean so far. The ocean itself, as well as life below the seafloor, is still a mystery. The sediments that are underlying our oceans are home to different microorganisms that exist even at depths of 1.5 miles beneath the seafloor. There are microbes hidden deep inside volcanic rocks below the seafloor off of the parts of the Pacific, hidden under 870 feet of sediment. The biosphere under the seafloor is growing extremely slowly compared to life on the surface. Cell division happens every 10 to 1,000 years. Something's different about the Earth's axis. Climate changes and melting glaciers, mostly in the regions like the Himalayas and Alaska, made the axis shift. Our planet has two kinds of poles. Are the south and north magnetic poles. They affect things such as drift and navigation. The axis that the Earth is spinning around is another kind of pole. It shifted a little bit over time, but we don't know exactly why. Researchers realize there are moving masses of water, pushing the Earth's axis eastward. Take a basin of water as an example. If you're moving it back and forth, sloshing makes the water move its weight all around. A similar thing is happening on a planetary level. No matter how large an earthquake is, no human could ever feel an earthquake on the opposite side of the Earth, although some people claim they did. In 2013, there was one near the Kuril Islands with a magnitude of 8.5. It went around 400 miles deep. It was so strong, people in Australia reported they could feel the ground shaking. The strongest earthquake happened in Chile in 1960 with a magnitude of 9.5. The rupture zone stretched from 311 miles to almost 620 miles along the country's coast. Earthquakes with a magnitude of 10 or higher can't happen. The magnitude depends on the length of the fault where it occurs. The longer the fault, the bigger the earthquake. A fault is a break in a part of the planet's crust. It has rocks on both sides, and they move past each other. We haven't found a fault long enough to generate earthquakes with a magnitude of 10 or more. If it happened, it would extend around most of our planet. An earthquake with a magnitude of 12 would require a fault larger than our planet. One side of our planet is getting colder than the other. The Earth has a system that keeps it warm from the inside, a red-hot liquid interior deep below the surface. It spins and, at the same time, generates a magnetic field and gravity. That way, the Earth's core holds the atmosphere closer to the planet's surface. The Earth also absorbs heat from the sun, mostly on the surface. The heat doesn't spread equally on all parts of the Earth. One side of the planet, the Pacific Hemisphere, is losing heat more quickly than another, the African Hemisphere. This happens because land traps more heat than the surface under the ocean. The seafloor is way thinner than the landmass. Also, the temperature caused by the heat coming from inside the Earth is getting lower because of huge amounts of cold water above it. Clouds are not just like some fluffy distant pieces of cotton. They weigh more than 1 million pounds and help regulate our planet's temperature. If you take all the water droplets in clouds and bring them to the surface, you could cover the planet with a liquid layer as thin as a human hair. It doesn't seem like a lot, but this water is crucially important for climate. We'd have warmer temperatures if it weren't for the clouds.
Imagine a world of seething hot metal where iron and nickel dance in a fiery inferno. This is the inner core, the heart of our planet. But what if this very heart was changing? The latest research suggests that the Earth's inner core may be slowing down and even reversing its rotation. Is this a sign of the end of times? Will the Earth come crashing down on itself? Let's find out. Imagine you have a giant onion, and every layer represents a different layer of the Earth. The center of this onion, the part you can never reach, represents Earth's core. It's like a mysterious land that no one has ever set foot on, yet scientists have been trying to uncover its secrets for centuries. Imagine diving deep into the center of the Earth. beyond the crust, the mantle, and finally 1,800 miles below the surface where you'd reach the inner core. It's a ball of seething hot metal made up of solid iron and nickel, and it's so hot it glows a brilliant white. It's also surrounded by a liquid outer core. This mysterious place is unlike anything else on our planet. And get this, it's spinning on its own axis. The inner core is like a fire tornado that's constantly swirling, generating heat and energy from the inside out. But why is it so important to study this little piece of the Earth? Well, it's responsible for creating our magnetic field. This magnetic field is important to study because it protects us from harmful radiation from the sun. It's created by the movement of molten metal in the Earth's outer core and the spinning of the Earth. These movements generate electrical currents, which then create the magnetic field. It's like a shield that protects us and helps us keep our planet healthy and safe. But there's still so much we don't know about the inner core. For example, how did it form? Scientists believe it started to solidify about 1 billion years ago. But why did this happen? What was the trigger? Or, for example, what about the inner core's crystal structure? It's thought to be a type of iron called hexagonal close-packed iron, but we still don't know if it's actually the case. In other words, we may have many theories, but unfortunately, there's no way to confirm them, at least for now. So how do scientists study the inner core if no one can go there? They use seismology. Seismology is like a sonic scanner for the Earth. You send sound waves through the Earth and measure how they bounce back to see what's inside. That's basically how we discovered the inner core way back in the 1930s. Imagine you're listening to the sound waves with your special seismology machine. Suddenly, you hear a strange sound like a ping. It's different from the other sounds you've been hearing, and you can't explain why. You keep listening and you hear the ping again and again. You start to realize that this ping is happening every time the sound wave hits the Earth's center. You study the data more and more, and finally, you figure it out. The Earth has a solid core. This discovery was a big breakthrough and helped us better understand what's inside our planet and how it works. Right now, scientists also use something like this to study what's inside our planet. When earthquakes occur, waves travel through the Earth and bounce off different layers, including the inner core. By studying these waves, scientists can learn about the inner core's properties, such as its density and temperature. They're basically solving a mystery by piecing together tiny clues. And every new discovery brings us one step closer to understanding it. The inner core is a unique and fascinating part of our planet. It's a place where the laws of physics work in different ways than they do on the surface. And it's a place where scientists are still trying to unravel its many mysteries. And here's one of them. For some reason, the heart of our planet is about to stop spinning. A new study about this was published in Nature Geoscience. It was made by the researchers at Peking University in China. It has revealed a huge twist. The scientists found that the inner core spin rate has slowed down significantly. It's something that no one expected, but according to the results of their study, the slowing down began all the way back in 2009. And that's not all. Their results also suggest that the inner core may be reversing its rotation. That's right. This hot ball of iron and nickel that has been spinning around for millions of years may be slowing down and changing direction. It's like when a spinning top starts to slow down, except this is happening in the center of our planet. Scientists have been puzzled over the discovery for quite some time now. So, what does it all mean? And why is this happening? Well, it turns out that there might be a larger pattern at play. The scientists believe that this change in the inner core's rotation may be due to the influence of Earth's mantle and the magnetic field of Earth's outer core. The mantle and the outer core are affecting the inner core, which is causing its spinning rate to slow down and potentially change direction. Before this study, scientists thought that the inner core was spinning faster than the Earth's crust. However, this new information suggests that the inner core may be slowing down due to the gravitational effect of the Earth's mantle and the magnetic field of its outer core. But here's where it gets even more interesting. When researchers took a closer look at data stretching all the way back to the 1960s, they discovered that the rotation of Earth's inner core was consistent from the late 1970s to the early 2000s. Before that, they found that another possible slowing down or reversal event may have occurred in the early 1970s. It's like the inner core spin is like a roller coaster ride, speeding up, slowing down, and possibly reversing course over a period of time. The researchers estimate that these switches occur every 7 decades or so, which is pretty wild. But why is it happening? Unfortunately, we still have no idea. The exact reasons for why the Earth's inner core sometimes stops and starts spinning in another direction aren't yet well understood. However, scientists believe that it may be due to complex interactions between the solid inner core and the surrounding molten outer core. A lot of different things can be at play here. The changes in the temperature, pressure, and composition of the core, as well as the movement of material within the core itself, and so on. Also, as we said before, the Earth's magnetic field and the gravitational forces from the surrounding mantle might also play a role here. We need further research to fully understand the mechanisms behind the inner core's rotation changes. So, is the world ending? Fortunately, no, not just yet. While the inner core is changing direction right now, it's not the end of the world as we know it. And even though findings may seem like a huge deal, life on Earth's surface hasn't been impacted much, if at all. In fact, it's just a fascinating part of the Earth's inner workings that we're learning more about every day. So, you can say with relief, nothing cataclysmic is happening. Moreover, according to Hrvoje Kalsic, a geophysicist at Australian National University, the inner core is now more in sync with the rest of the planet than a decade ago when it was spinning a bit faster. All in all, this new study has added a strange twist to the story of Earth's inner core, and scientists believe that there's still much more to discover about this mysterious place. Who knows what other secrets lie in the heart of our planet? The possibilities are endless, so let's keep researching and enjoy our time on this amazing planet.
Tell me the truth. You probably think that Earth's magnetic field is caused by a big ball of solid iron in the middle of the planet, right? Yep, I mean the inner core. But the problem here is that in the inner core, the temperatures are so high that the very magnetism of iron itself is changed. Once such a temperature, which is called the Curie point, is reached, atoms aren't able to align to a magnetic point anymore. So, in reality, Earth's magnetic field is created by the swirling outer core, and magnetism there is more than 50 times greater than it is on the surface. The liquid iron in the outer core conducts electricity perfectly, which helps it create electrical currents driving the magnetic field. Without it, our planet wouldn't be able to hold onto its atmosphere. As a result, we'd lose our main protection from extremely dangerous space radiation. But it wasn't the outer core that surprised us not so long ago. Scientists say Earth's inner core has likely stopped rotating relative to the mantle and the surface of the planet. Even more exciting, it could even go into reverse. But let's look into the details. Earth is formed of the crust, mantle, and outer and inner cores. The solid inner core is about 3,200 miles below the crust. It's separated from the semi-solid mantle by the liquid outer core. Yep, the one thanks to which we have the magnetic field. And since this outer core is liquid, it allows the inner core to rotate at a speed different from the speed of our planet's rotation. Earth's core has a radius of 2,200 miles and is almost as large as Mars. It mostly consists of iron and nickel and makes up around 1/3 of Earth's mass. The spin of the inner core is powered by the outer core. It turns out that the slowing of the core started in 2009. Since that time, seismic records, which had previously been changing continuously, have shown little difference. And it makes scientists conclude that the inner core's rotation has paused. But we're nowhere near the scenario of a disaster movie. Apparently, the inner core taking a temporary break is part of its 70-year-long cycle. During this cycle, the core switches directions every 35 years or so. This might influence Earth's magnetic field and the length of the day, but some researchers are skeptical about it. And some scientists even go as far to say that the inner core isn't moving at all. Okay, but what would happen if Earth's core indeed stopped rotating? Well, if it was the solid inner core, the answer would be nothing dramatic. Even if it didn't just reverse the direction of its movement, like it's doing at the moment, but stopped altogether, it would just impact the speed of Earth's rotation. It'd slow down, making our days longer. Plus, with time, it could probably degrade our planet's magnetic field, and it would be bad news. But not as bad as they would be if the outer core stopped spinning. As you already know, without this layer's rotation, Earth would have to kiss its magnetic field goodbye, and that's how the downfall of the planet would begin. Things would start getting shaky. The tectonic plates would begin to slam into each other. You know, like when you're going by bus and the driver suddenly hits the brakes and you end up flying into other unfortunate passengers? Yeah, like that. The sudden collision of tectonic plates would trigger destructive earthquakes along the plate boundaries all over the world. They would wipe buildings, bridges, and roads off the face of the Earth. Water systems, electricity, and phone lines would also be destroyed. But the worst would be yet to come. Without the protective magnetic field, cosmic radiation would start hitting the surface of our planet. These high-energy particles coming from the sun would come in contact with oxygen and nitrogen in our atmosphere, effectively destroying our ozone layer. This would allow even more cosmic rays to reach the surface of Earth. The radiation would damage all kinds of electronic devices and disable power grids. And the consequences would be disastrous, not only for people, but for all forms of life on Earth. The stationary core would make navigating the planet more difficult. People would have to start using trail maps again, since compasses would become useless. It would also make it harder, if not impossible, for migratory animals to find their way. Birds would keep losing directions, and turtles would fail to find beaches where they used to lay eggs. Luckily, we don't need to worry about this kind of apocalyptic scenario. The planet's outer core is very unlikely to stop anytime soon, if ever. Now, do you want to find out something cool? Then listen to this. Our planet's inner core has a core of its own. Scientists have made this discovery just recently. They've learned that this core in the core could have developed around 500 million years ago as a result of some dramatic geological changes. What about other planets? Do they have the same cores as Earth? Let's look at Mars, one of our planet's closest neighbors. Its heart is the size of the Moon. It's also almost twice as dense. Scientists made this conclusion after they got some data about the first observed Marsquake and meteorite impact. Both these events were captured by NASA's InSight lander, which had been monitoring seismic activity on the red planet for 4 years. The researchers also estimated that Mars's core is probably made mostly of a liquid iron alloy with a smattering of hydrogen, oxygen, and carbon. One day, Mars probably had a nice rotating core that supported the planet's magnetic field. There could be warm oceans swarming with life. But then, something must have happened, and on one terrible day, the red planet's core froze in place. It could have led to the weakening of Mars's once strong magnetic field. Its atmosphere was taken away by powerful solar winds, hitting the planet at a speed of several hundred miles per hour, and the red planet turned into a lifeless, dry desert. Now, what about gas giants? Let's take the largest and the most massive planet in the solar system, Jupiter. It's twice as massive as all other planets of the solar system combined. Almost 1,300 Earths could fit into this huge thing. Jupiter also has the shortest day in the solar system. It lasts a mere 10 Earth hours. At the same time, the gas giant needs 12 Earth years to complete an orbit around the Sun. Jupiter most likely appeared at the same time when the rest of our solar system formed, about 4.5 billion years ago. Probably the coolest thing about this gas giant is that it has the same ingredients as a star. But unfortunately, or should I say luckily, it hasn't grown massive enough to ignite. Scientists don't know for sure what Jupiter's core looks like. According to most theories, the gas giant has a dense core made up of heavy elements. During its formation, it was probably a collection of debris, icy material, and other small objects like comets and asteroids zipping around. Thanks to their mutual gravity, these bits of matter clumped together, forming larger chunks which later turned into Jupiter's core. At one point, it became massive enough to start attracting hydrogen and helium. More and more gases accumulated around the core until what we today know as Jupiter appeared. There's also a possibility that Jupiter doesn't have a core at all, or it might have existed once, but since then, it's eroded away. Hopefully, we'll find out the answers to these questions soon enough, since Juno, NASA's space probe, is orbiting Jupiter, collecting data about its gravitational and magnetic fields. So, what about the gas giant's magnetic field, you may ask? Does it even exist? Oh, don't worry. Jupiter is surrounded by a ginormous magnetic field called the magnetosphere.
Today, we're going to work our core, so get ready to sweat. Oops, sorry, wrong core. Hey, we've traveled far and wide, down to the Earth's inner core and up into outer space. But what if we could combine these adventures and find out what hides in the innards of other planets and moons in the solar system? With the help of this interstellar hyperdrill, we can achieve that, at least in part. Coordinates are in, all systems ready, and our first destination is the Moon. Our moon, in fact. We land on its gray and desolate surface under the black sky. No blue here because there's very little atmosphere to disperse the light. The drill starts working, and we first go through the outer layer of the moon, the crust, just like on Earth. We're on the sunny side, so the thickness of this layer is only 43 miles. But were we to land on the dark side, it would be more than twice as thick. The moon is a rocky body, so its crust is largely made of silicon, iron, aluminum, calcium, oxygen, and magnesium, with much smaller amounts of other elements. Further down, we find the mantle, and it's a long and tedious journey through. This layer is about 850 miles thick. It gets hotter as we go deeper, finding composite minerals, pyroxene and olivine. They're made of iron, silicon, oxygen, and magnesium in different proportions. Finally, we break through the hard layers and into the semi-molten outer core. Another journey of about 93 miles ahead through this scalding swamp. And we dive into the iron ocean of the liquid core shell. It's nearly 60 miles thick, and the molten metal threatens to evaporate us. But this drill was made to sustain an extremely heavy onslaught. And that's how we finally come to a sudden halt. In the deepest reaches of the moon, there's a solid iron core, which is 150 miles thick. We could drill through it, but it would be unnecessary. So we just set the flag here and skip to the next planet on our drilling list. And it's Mercury. It was hot deep inside the moon, but on the surface of the smallest planet in the system, it's even hotter. That's because it's so close to the sun, of course. Alright, let's drill. Mercury has a pretty thick outer shell, which is both crust and mantle, going about 250 miles deep. Not the most fascinating journey, it's not unlike the Earth in many respects. But then, the drill stops, ramming into a solid metal wall. It's Mercury's core, which has a diameter of over 2,500 miles. It takes up to 85% of the planet's overall diameter. No use trying to drill through this one. It's fully metal and extremely dense. Skipping to the next planet, and we're on Mars now. Oh look, it's sunset here, and the sun is making the sky hazy blue. But you know the drill. I mean, we're here to drill, so that's what we do. Mars's crust is quite thin compared to Earth's, just 6 to 30 miles deep. Its composition is much the same though: iron, aluminum, calcium, potassium, and magnesium. That's one of the reasons why humans are looking to colonize the red planet one day. It's very similar to our own. We're very quick to drill through the first layer, and the second one, the mantle, is now upon us. It's a hard and rocky layer about 1,100 miles thick. Thanks to its size, Mars isn't seismically active any longer. There's simply no magma boiling close underneath the surface of the planet, making it silent and docile. It's a long dig, but we finally come to a screeching halt, bumping into the core. A ball of iron, nickel, and sulfur with a diameter of 2,000 to 2,600 miles. This core is bigger than that of Mercury, but the planet itself is larger too, so it figures. Okay then, our next stop is even more interesting, because it's Jupiter. This gas giant has a mass twice that of all the other planets in the solar system combined. And we landed right in the middle of an ocean. The ocean, I dare say, it's the largest one in the whole system, and it's made of liquid hydrogen. The drill goes smoothly through the surface of the planet because there's no rock or hard metal here, only gas and liquid. But the shaking, yikes! The pressure on this planet is more than just huge, it's unimaginable. The drill is barely able to withstand it, and as it's going deeper, the pressure's becoming higher too. We've reached Jupiter's core, and it's nearly too much to bear. The temperature here is about 90,000 degrees Fahrenheit, and the core itself is not solid but liquid as well, kept together by the immense pressure from all sides. The drill starts to rattle. Bad sign. Let's get out of here before it breaks. Whew! No winds, no pressure, no heat. All around us is a vast icy wasteland, crisscrossed by ridges and reddish bands. It's Europa, one of Jupiter's most promising moons. As we drill through the ice, let me explain. Europa is one of the candidates to have extraterrestrial life in the solar system, and it can be found right beneath the icy shell through which we're now digging. It's only 10 to 15 miles thick, while down below is an enormous saltwater ocean, twice bigger than all of Earth's oceans combined. The deepest point on Earth is Challenger Deep, and it's a bit over 6 miles down. The ocean on Europa, on the other hand, can be up to 100 miles deep. Who knows what can be lurking in that deep, dark sea? Anyway, we travel fast through the water and finally reach the bottom of the ocean. The mantle starts here, and it's made of rock, just like on Earth. And not much deeper in, we find the metal core of the moon. Europa is a little smaller than Earth's moon, so it's no surprise we reach its center pretty fast. Okay, skip drive on. Let's go further. Oh, I'd rather we drill in as fast as we can. Just look around, it's blazing here. We're definitely on Io, another moon of Jupiter, and the most volcanically active world in the solar system. Look, that volcano is twice the size of Everest, and it's erupting right now. Thankfully, we're under Io's surface already, but that's not to say we're safe. It's all molten down here too, mostly yellow and brownish hue, due to the huge amounts of sulfur. The stench must be horrible. Anyway, the most peculiar feature is that both inside and outside, everything's always on the move on Io. Jupiter and its other moons create tremendous tidal forces, making the surface of Io swell over 300 feet up and down. Like the largest tsunamis on Earth, only here it's not water but rock. The deeper we go, the calmer it gets though, until we're finally at the iron core. It's still hot here, but at least there's no shaking and swelling like above. Let's put up another flag and go to the next point. And that would be Saturn, the second largest planet of the solar system and the one best known for its spectacular rings. Not the only one to have them at all, mind you, but we'll get to it. Now, as you've surely noticed, our drill is simply falling down through the gaseous hydrogen and helium, making up most of the planet's surface and atmosphere. No need to work here, just wait and hope the immense pressure won't crush our drill to a hunk of junk. At last, the pressures become so enormous that we find ourselves in the liquid hydrogen, and here we start diving. Soon we'll reach the solid core of Saturn. Ah, here we are. It's made of iron and nickel and is actually quite small compared to the rest of the planet. Well, the last destination awaits, so come on. And here we come, Neptune. The drill immediately deploys anchors because the winds here are extremely powerful. They reach speeds 5 times greater than the most devastating hurricanes on Earth. Neptune is covered in a pretty thin layer of hydrogen and helium, just like Saturn or Jupiter, but underneath, there's much more than that. It's hot, windy, and lonely here on the outskirts of the solar system. So let's dig already. Beneath the gases, there's suddenly a bubbling hot mass of water, methane, and ammonia. Phew! These substances are hot, despite Neptune being called an ice giant. The name comes from its core. Deep inside, where we're quickly headed right now, a small ball of rock and ice sits all alone. And despite the boiling temperatures above, the ice beneath is ever cold. Back in 2018, the biggest active underwater eruption ever happened, at least the one that we could officially record. Scientists followed earthquakes that struck the area in the western Indian Ocean off Madagascar. Between 2018 and 2021, over 11,000 earthquakes struck a small island called Mayan between Madagascar and Mozambique. The strongest one had a magnitude of 5.9. Until then, this area had been pretty peaceful. There had only been 2 earthquakes recorded over 50 years. Along with regular earthquakes, there were also some unusual seismic hums, like earthquakes at pretty low frequencies, forming deep underground. People couldn't feel those hums at the surface, but researchers around the world discovered them and realized they were related to volcanic activity no one actually noticed coming. Something strange happened. That underwater eruption created a giant skyscraper-sized volcano. This new underwater volcano turned out to be around 1.5 times the height of One World Trade Center in New York, and almost 10 times bigger than the Statue of Liberty. The area where it appeared had been explored in 2014, but it was almost flat, peaceful, and empty back then. Now, there is an actual volcano nearly 8,500 feet below sea level. The volcano gets its magma from a super profound reservoir located nearly 34 miles underground. It's the deepest reservoir of volcanic magma that we know about. The Earth has layers, and the middle one is kinda chunky. It's very much like peanut caramel filling many chocolates have. Research shows there are probably hunks of oceanic crust deep inside the Earth's liquid mantle. They're stuck there, creating large lumps in something that was supposed to be a smooth layer. Our planet has a rigid outer layer. It includes a hot upper mantle and cracked crust. The hot mantle moves and churns all the time, making the crust at the surface move too. This way, the oceanic crust dives into the depths and makes huge magma plumes go up toward the planet's surface. Scientists even found an ancient piece of the Pacific Ocean hundreds of miles underneath China. Those are the old remains of the Pacific seabed from long ago, and they were pulled downward below Earth's surface into the mantle transition zone. This rocky slab that used to be at the bottom of the ocean is made of the crust and some solid parts of the upper mantle. Most of the volcanic activity on our planet happens where we don't even see it, under the surface of the ocean. About 70% of all volcanic activity happens in the oceans, and mostly in the area of the South Pacific, with over 1,100 volcanoes squeezed into that area. Coastal cliffs, mountain changes, soils, and sediments that line valleys. These are only a small portion of the rocks on our planet. Oceans hide so much more deep down below the Earth's surface. In between the Earth's surface and its core is the mantle. It's a warm, thick layer of rock that moves and flows constantly. Some hundreds of miles below, there's a place where diamonds grow. As they form, they go through high temperatures and pressure, after which they eventually freeze. That way, when they arrive at the surface, scientists can explore their structure, find out how they formed, and understand better what's going on in the depths of our planet. Thanks to diamonds, they realized the mantle was very wet, and it possibly contained much more water than all the oceans on Earth. Our planet is eating up its own oceans. As its tectonic plates move, dive, and go beneath one another, they drag huge amounts of water into the Earth's interior. The water beneath the surface of our planet can help with developing magma and lubricate faults, which actually makes earthquakes more likely to happen. Water is actually stored in the minerals. It gets incorporated into the planet's crust when new oceanic plates form. They go through the process of bending and cracking as they grind under other plates, and huge amounts of water then go deep into the crust and mantle. Scientists research an area that's 18 miles under the surface. They realize these zones pull 3 billion teragrams, which is more than 2 billion pounds. Any ocean is like a whole new world. There are incredible sceneries below the surface, magnificent waterfalls, lakes, and rivers. There are thick layers of salt beneath the seafloor, and rivers and lakes form because seawater goes through those layers and dissolves them, creating something that resembles pools. The dissolved salt makes the surrounding water denser. That water then settles there, which eventually forms underwater lakes or rivers. But there are also mountain chains, trenches, canyons. There's a canyon in the Bering Sea with more than 8,500 feet of vertical relief. This makes the Grand Canyon look way smaller than it is, since the underwater canyon is nearly 2,500 feet deeper. Deep parts of the ocean are really cold. The temperature of the water can be about 40 degrees, but at the bottom, water can get boiling hot. There are hydrothermal vents in the seafloor. Those are the hot springs located at the edges of tectonic plates. The water they release can reach a temperature of up to 750 degrees Fahrenheit, but the pressure at such depths is very intense. So intense, no human being can handle it. Still, it's the pressure that keeps the water from boiling. Ocean depth is on average 2.3 miles. Light waves can still enter at 3,280 feet, even though it's in a very small amount. So all the mysteries hidden below that point remain in total darkness. The actual illuminated part of the ocean goes until 600 feet. Even though the sun gives us light, most of our planet is dark all the time. It's all because of the oceans, covering over 70% of our planet. The loudest sound that came from an ocean, and of the loudest sounds ever recorded, came from an ice quake. It was so loud, researchers picked it up by sensors more than 3,000 miles away. There was a seismic activity that made frozen ground break down. The Antarctic ice sheet is bigger than the continental part of the United States and Mexico together. A big iceberg from Antarctica holds over 20 billion gallons of water, which could make a 5-year water supply for 1 million people. Humans can generally drink sea ice, although we can't drink seawater. As time goes by and the ice ages, the brine trapped between ice crystals drains out. That way, ice becomes fresh enough to consume it. If all the ice sheets and glaciers we have on the Earth melted at the same time, the sea level would rise another 260 feet, which is just a little shorter than the Statue of Liberty, the height of a 26-story building. Clams live long enough to tell us more about oceans past. Ancient mollusks can live for more than 500 years. To learn more about a tree, you can use its rings to see how old it is. To learn how old a mollusk is, you can examine its rings within the shell and tell. This is also how scientists get information about the ocean, climate, and whatsoever. Clams can help take a look at what happened about 1,000 years ago. The Earth doesn't have 4 but 5 oceans now. The new one, called the Southern Ocean, was officially recognized only a few months ago. It borders the Atlantic, Pacific, and Indian Oceans, so scientists couldn't agree if it's really a new ocean or just part of the colder regions of these 3. We don't only divide oceans on maps. Each has different conditions for unique marine species. For example, the Southern Ocean has leopard seals, orcas, minke whales, emperor penguins, and other animals that live in cold, icy seas. It's also home to krill, small creatures that look like shrimp and are food for many bigger animals that live there. Life on our planet started about 3.5 billion years ago. I wasn't around then. It's still a mystery how and when exactly, but some theories say life could have first emerged in the depths of the ocean. A few years ago, scientists found microscopic tubes and filaments within rocks formed about 4 billion years ago. These rocks are fragments of ancient oceanic crust. Also, these tiny tubes and filaments are similar to microbes that can still be found on hydrothermal vents in deep parts of the ocean. The idea is these living cells found conditions to stay alive in tiny rocky pores inside the chimneys of those vents, and started the amazing adventure of the evolution of life on our planet. The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Well, be patient, we'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia, and these movements are very unpredictable. But it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year. And recently, the pole crossed the international date line, moving toward the eastern hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving, but is also getting weaker, by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicates changes in the global geometry of the magnetic field of our planet, and they may point to the beginning of the field reversal too. That's what the flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving through the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic radiation, which otherwise would be extremely dangerous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and the magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They're called coronal mass ejections, or CMEs. They're ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMAs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for the Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling towards our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they've been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geological point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Such events tend to change the concentration of ozone in the atmosphere. In any case, scientists can't say for sure when the next field reversal will happen, but they keep mapping and tracking the movement of our planet's magnetic north. By the way, the Earth isn't the only planet with a magnetic field. Gas giants, like Jupiter, also have a conducting metallic hydrogen layer that generates their magnetic fields. Jupiter's internal magnetic field prevents the solar wind from interacting directly with the planet's atmosphere.
How would you describe the shape of the planet we live on? It's definitely round, but it's not a perfect sphere. Because of the force of Earth's rotation, it's slightly flat on the north and south pole. But there's more to it. The planet's rotation causes its sides to bulge outwards. The best term to describe our home planet is ellipsoid. Earth is nothing more than an oversized lumpy potato. These are the words of Atraji Ghosh, a solid Earth geophysicist from Bangalore. She and her team have been studying something called the Indian Ocean gravity hole. Sounds like the scenario for a science fiction movie, but it's very much real. We think of gravity as something consistent. If you drop a pen from your hand in Los Angeles and in Perth, they're going to fall to the floor at the same time. Well, this is not completely true. Gravity is connected with the mass of a celestial body. Astronauts on the surface of our moon don't walk, but move in hops. That's because Earth weighs 81 times more than the moon. Less mass means less gravity. Earth is more massive, so it has a stronger gravitational pull. But there's a catch. All this mass isn't distributed evenly across the planet. As a result, gravity varies as well. NASA has been mapping Earth's gravity field since 2002 using twin GRACE satellites. The maps they produced show where gravity is stronger and where it's weaker. Mountain ranges such as the Himalayas contain a lot of mass. This means they generate a stronger gravity field. The opposite happens in ocean trenches. The deepest of them is the Mariana Trench in the Pacific Ocean. You could almost stack 2 Mount Kilimanjaros inside it. The low concentration of Earth's mass below it means that the gravity field here is weaker. Places on the globe where huge chunks of mass are missing are called geoid lows. A geoid is an imaginary surface that follows the outline of sea levels around our planet. Imagine the Earth without any land. That shouldn't be too hard since the nickname of our home is Blue Planet. Now draw a curvy line along the surface of the oceans, and you get a geoid. In reality, the line stretches across oceans, as well as land masses. Scientists use this imaginary line to calculate the depth of tremors or objects that occur underground. When the wavy line goes down, that's a geoid low. The biggest of them sits at the bottom of the Indian Ocean. The first to discover it was a Dutch geophysicist in 1948. He was performing a gravity survey from a ship. The man noticed that sea levels dipped over 320 feet below the global average. The gravity hole got the official name Indian Ocean Geoid Low. It spans well over 1 million square miles off the southern coast of India. If you went out at sea in the middle of the gravity hole, you wouldn't notice much, just an endless ocean as far as the eye could see. The only way to measure the dip in gravity is through extensive geophysical measurements and calculations. The concept of a gravitational hole existed for nearly 2 centuries in the scientific community, but researchers could study it in high detail only after satellite measurements became possible in the late 20th century. A team of Indian scientists was determined to explain the anomaly that had been puzzling geologists for decades. They used supercomputers to simulate the seismic activity that formed our planet. A total of 19 simulations revealed how tectonic plates moved across the span of over 140 million years. This was during the Cretaceous period, the time when T-Rex roamed the Earth. Nearly a third of the possible scenarios produced a geoid low, similar to the one in the Indian Ocean. The most important factor in these models was the presence of magma plumes. These are places inside the Earth's mantle where lava flows upwards. The mantle sits between the planet's outer core and the thin crust we walk upon. The magma in the mantle plume is hotter than the surrounding rocks. The heat it generates melts and thins the crust. This creates hotspots that are brimming with volcanic activity. Yellowstone National Park and the Hawaiian Islands sit atop such hotspots. The Indian team of scientists linked the presence of magma plumes to the formation of the geoid low. Their source was an ancient ocean that disappeared tens of millions of years ago. It was located where the Himalayan mountain range sits today. Evidence of this lie in the marine rocks researchers found on the world's tallest mountains. The oceans ceased to exist when India's landmass separated from the supercontinent called Gondwana. It drifted north and merged with the rest of the Asian continent. At the time, the Eurasian supercontinent was called Laurasia. The Indian tectonic plate went down inside the mantle. It ended up under the African continent. This landmass contained a lot of crystallized material which was quite dense. When the sinking plate of the former ocean reached it, plumes of magma spilled out. As a result, low-density materials ended up closer to Earth's surface. Density is used to calculate mass, and if you remember our lesson in physics from the beginning of the video, less mass translates into a weaker gravity field. Scientists believe this is how the geoid low in the Indian Ocean formed some 20 million years ago. At this point in prehistory, the Earth looked a lot like it does today. There were vast grasslands, and whales swam in the seas. Geophysicists who created the computer model cannot tell for sure what will happen in the future. Ghosh thinks it's possible that the gravity hole in the Indian Ocean will remain in place for a long time. But plate movements can also cause the anomaly to fully disappear in the coming eons. Earth's tectonic plates are constantly shifting. They define the shape of our continents and oceans. Experts study plate movements to get a picture of how our world looked millions of years ago. However, telling Earth's geologic future is much more complex. The gravity hole in the Indian Ocean is the biggest, but it's not the only one in the world. Other areas with low gravity include the island of Cuba and the Bahamas. On the opposite side of the spectrum are the Philippines. Here, gravity is stronger than normal, but the poles are the places with the strongest pull to them. They are the closest to the center of the Earth. If you stand directly on the North or the South Pole, you are 3,950 miles from the planet's core. At sea level on the equator, this distance increases by more than 13 miles. Earth's gravitational field also has an effect on your weight. At the equator, you weigh 1% less than you do on the poles. The South Pole is maybe more suitable for this experiment because there is actually ground there. But gravity is the strongest at the North Pole in the middle of the Arctic Ocean. This is where scientists in 2013 recorded the highest gravitational acceleration on the planet. This is the rate a falling object speeds up in free fall. The acceleration depends on the strength of gravity. When a team of researchers from a university in Perth set out to map these gravity changes, they discovered something interesting. Gravitational acceleration was the highest at the surface of the Arctic Ocean. This is something they expect to find, but the location of the lowest acceleration point amazed them. It wasn't on the equator as they assumed. The spot lay more than 600 miles south of it at Mount Huascarán in Peru. Scientists believe that the mountain's height had an effect on the phenomenon. This peak in the Andes is the highest point in the South American country. Hypothetically speaking, if a human falls from a height of 330 feet here, they will reach the ground 16 milliseconds later than if they performed the same stunt in the Arctic. Thousands of years ago, a huge meteor weighing 2 million tons crashed into Earth at a speed of around 56,000 miles per hour. Sounds like a big deal, and it was. It actually created Lonar Lake in Maharashtra. When you see it from above, it might look like any other lake, but the sand there is magnetic, and it makes compasses go haywire. First off, it's a soda lake. Nah, it's not filled with Coke. It's just another name for an alkaline lake. The pH levels there vary from 9 to 12, whereas humans enjoy ranges from 6.5 to 8.5. So it's not really advisable to bathe there, not to mention to drink such water. There's a little round dip about 2,300 feet away from the main lake, which folks think was made by a piece of the main meteor. Near this lake, there's a Hanuman temple that has an idol carved from rock, and it's said to have some pretty strong magnetic vibes. Also, local farmers are draining water from Ambar Lake. Sometimes people refer to this lake as Chota Lonar, which means Little Lonar. This nearly perfect oval is one of only 2 natural craters in the world made entirely from basalt, a dark, finely textured volcanic rock. The water there is 7 times saltier than ocean water, and sometimes the lake can turn pink due to particular bacteria. Whenever you open up a tap to fill a glass of water, water goes from top to bottom because gravity, duh. It's hard to imagine it acting the other way around, but turns out there are many waterfalls that can defy gravity and go in the opposite direction. That's called a reverse waterfall, and it happens when super strong winds whip through a waterfall, pushing the water back up. It's especially common for those windy fall and winter months. You usually need winds of at least 46 miles per hour to see this cool trick in action. It's actually not as rare as one may think, and you can find these wild reverse waterfalls all over the globe, from Australia to India, Japan, the UK, and the US. In Australia, in areas like Sydney, the Central Coast, and Royal National Park, winds around 43 miles per hour have been known to turn waterfalls upside down. Yep, it's all about the wind going this fast. Please put aside all those weird myths about Australia being in the southern hemisphere, like the one about the water in the toilet flushing in the opposite direction. This is nothing but an urban myth. In India, near Mumbai, and in places like Sandan Valley and Amboli Hills, waterfalls get blown upward during the monsoon. And if you're ever in the Faroe Islands, you can witness this unique phenomenon happen regularly due to the region's geography and fierce winds from the North Atlantic. Magnetic Hill in Ladakh, India, is a fascinating spot, sitting at about 14,000 feet high, right along the Srinagar-Leh Highway, just 16 miles from Leh City. It's known for a quirky gravitational trick where parked cars mysteriously roll uphill when left in neutral, defying logic and catching the attention of visitors from all over. Locals have their own myths, viewing it as a path between heaven and earth. You'll want to stop by between June and September when the weather is just right and the optical illusion effect is at its peak, typically from 8 a.m. to 5 p.m. In Brazil, there's this street called Rua do Amendoim that seems to defy the laws of physics, leaving many puzzled as they walk or drive down it. Locals affectionately call it Peanut Street, and there's never a shortage of parking spots. That's mainly because if a car is parked without the emergency brake, it starts to roll uphill all on its own, picking up speed as it goes. People have all sorts of wild theories about why this happens. Some say the hill is haunted, while others think there's a huge iron ore deposit beneath it pulling cars up like a magnet. But believe it or not, the truth is that this strange occurrence is just an optical illusion. The street looks steep, but it actually has a slight dip. So, while it seems like cars are rolling uphill, they're really just going downhill. Still, that hasn't stopped folks from filming countless videos of this quirky sight. Located on the beautiful Black Sea coast, Ureki is a chill beach resort town known for its unique magnetic sands that are all about health and wellness. These sands have been getting attention for their healing powers since the 1800s. Helping people tackle various health issues. Ureki's magnetic sand is packed with minerals like magnetite and quartz. It's got an unusual magnetic content of about 23%, making its magnetic field way stronger than that of regular sand. The Hessdalen Lights are mysterious glowing orbs seen in a 7-mile stretch of the Hessdalen Valley in central Norway. These lights have been popping up since at least the 1930s and can be spotted both day and night. They usually shine in bright white, yellow, or red and can hover, move quickly, or sway gently. Their appearances can last from a few seconds to over an hour. Though there were many sightings, especially between 1981 and 1984, the frequency has gone down to about 10 to 20 a year as of 2010. Various groups, like Project Hessdalen, have tried investigating these lights since 1983, using methods ranging from field studies to scientific research. As for what these lights actually are, no one really knows for sure. Some sightings have been explained away as things like car headlights or astronomical objects. One theory suggests they might come from a chemical reaction involving airborne dust from local mines. Another idea is that they could be clusters of particles interacting in a specific way due to the area's geology. Some researchers have even proposed that the lights might be a result of piezoelectricity due to certain rock types in the valley. Other theories include complex interactions between electromagnetic waves and dust, which could explain the light's unique shapes and colors. Saharan dust, which once even made its way to parts of the UK and left a red layer on cars, is full of naturally magnetic materials. On September 7, 2023, some folks noticed their cars were covered in reddish flecks because of the dust blown from the Sahara. A video making the rounds on Facebook showed someone using a magnet to lift the dust off their car. One commenter even got pretty heated, saying, "If you want to know what fell down last night, just grab a magnet and check this out," insisting it was metal, not sand. Naturally, this sparked chatter about how the dust's magnetic properties could be linked to chemtrails. But guess what? Experts are clear that magnetism is actually normal for Saharan dust. According to Professor Barbara Marr from the Center for Environmental Magnetism and Paleomagnetism at Lancaster University, the dust carries a mix of particles from the African ground and some air pollution as it heads to Europe and the UK. The red color is due to hematite, a weakly magnetic mineral. Sure, the dust can pick up some human-made magnetic particles along the way, but scientists say those are usually way less abundant than the naturally occurring ones. The whole chemtrails idea, which suggests planes are intentionally spraying harmful substances, is based on conspiracy theories that have been thoroughly debunked. In short, the presence of magnetic particles in Saharan dust, like that of hematite giving its reddish tint, doesn't back up the chemtrail theory at all. Not having the internet in 2024 seems sorta abnormal, right? When we talk about internet access, it primarily comes down to wired connections, mobile networks, and satellites. Fiber optic cables connect most of the world, except Antarctica, and many small islands. Mobile networks are also widespread. Even in remote areas like the Sahara, you might find patchy access. For people in rural spots, satellite internet is often the best bet, even if it's slower. Still, there are a few truly isolated spots left. Deep caves like Georgia's Kerbera Cave are internet-free due to their depth. And under the ocean, signals struggle to get through, making internet access poor or non-existent. On September 16th of 2023, without warning, the Earth began to hum. A low, strange vibration reverberated through the crust. This set off seismic alarms all across the globe. For 9 days straight, the planet was pulsing with this horrifying rhythm, and scientists had no idea what was going on. Meanwhile, the total disaster was happening in Greenland. It wasn't an earthquake. They knew that much. They could tell it by the rhythm. Since we all live on giant tectonic plates, they constantly move and slide on magma like icebergs on water. Sometimes as they move, they can rub against each other or collide or break. In any case, all this causes an incredible release of energy that sends shock waves through the ground. That's when we feel the ground literally shaking, and it's what we call an earthquake. These vibrations we feel are called seismic waves. Seismometers pick them up as pings or rumbles. In a typical earthquake, they create a bunch of different frequencies. It's a crazy chaotic mix of low and high frequencies, like smashing every piano key. What was weird about the Greenland event is that the signals weren't like that at all. It was a steady, single-frequency vibration, as if some ancient machine was stirring beneath the earth. It's like one piano key being struck over and over, creating a doom-like, repetitive sound. Turns out, what they were hearing wasn't the noise of tectonic plates going wild. It was a phenomenon seismologists had never seen before. The days passed, and the mysterious noise just kept going. The vibrations repeated every 90 seconds, echoing around the world. The hunt for answers was growing more desperate. Seismologists had no idea what they were dealing with. They had to gather a huge international team of 68 people from 15 countries. All these scientists were gathering seismic data, satellite images, and doing some advanced math for several days, until they finally realized who the culprit was. Water. It all happened in a remote, desolate region of East Greenland. This place is full of fjords, narrow inlets of the sea between high cliffs, kinda like deep water-filled valleys surrounded by towering rocky sides. In this area, surrounded by jagged peaks and icy waters, the air was still. The landscape seemingly frozen in time. Nothing here changed much for years. Until one day. A colossal landslide has unfolded in the Dixon Fjord. One of those steep mountainsides towering over the fjord at almost 4,000 feet high collapsed in a massive landslide. Picture a huge chunk of this mountain crumbling and crashing down into the fjord below. This sent a deluge of rock and ice crashing into the water. The impact was just apocalyptic, 882 million cubic feet of debris. That's enough ice and rock to fill 10,000 Olympic-sized swimming pools, or 10 Great Pyramids of Giza. And all this nightmare hurled into the water with such force that it kick-started a tsunami about 360 feet high, taller than the Statue of Liberty, into the air. What's crazy is that this incredibly powerful wave was trapped in the fjord by narrow cliffs, unable to escape. It's like water sloshing in a closed bathtub. For 9 days, the mega tsunami continued to churn through it. That's why we heard this endless hum. It was a rhythmic back and forth of the water slamming against the walls. The shock waves were rippling deep into Earth's crust, vibrations so strong that they were picked up by seismometers around the globe. This was a phenomenon so rare, so unprecedented, that it left scientists stunned. It turned out to be a perfect storm of elements. A glacier, weakened by years of warming, could no longer bear the weight of the mountain above. This collapse was inevitable, and the chaos literally shook the Earth to its core. And people often hang out in this area with cruise ships passing by. We're lucky that no lives were lost in the disaster. It was a close call though. A tourist ship stranded in the area just 2 days before narrowly escaped the tsunami's reach by pure luck. But it doesn't mean there were no losses. The waves destroyed a nearby Inuit site, which was there untouched for over 200 years. They also swept away the huts at a research station that were about 43 miles away. The vibrations traveled from Greenland to the South Pole in less than an hour. That just shows how dangerous events like this can be. And this isn't the only place where such catastrophes are happening. In the beautiful California community of Rancho Palos Verdes, the ground is shifting so quickly that it's tearing homes apart. The land there has always been kinda unstable. It has some unique geology. It's built on soft, clay-rich soil and sits on a geological fault line, which makes it prone to landslides. This means that this land is prone to slow, natural shifting over many years, even when no crazy weather is happening. It's been like this for decades, but usually it's slow and pretty manageable, like about a foot a year. Imagine a tree that you played with as a kid moving 20 feet to the left as you grow up. For decades, residents adapted. They built their homes on adjustable beams. This helped the houses to move with the land, and that strategy worked well until now. Recently, things have been getting much worse in the community. Now, the land is moving by a foot in a single week. That would be like if the same tree moved almost 960 feet since you were a child. The past 2 years have also caused some heavy rains, and the weather has been getting worse. This increased water content in the soil. The land became heavier and more prone to rapid movement. Now, this once idyllic seaside escape turned into a disaster zone. Cracks have appeared in closets, gardens, and roads, growing larger with each passing day. Streets that were once smooth are now buckled and twisted, with roads turning into a crazy theme park. Houses that once stood firm are being ripped from their foundations, some of them split in half. One of the houses had its front door 8 feet off the ground. Entire neighborhoods have been plunged into chaos. Utility companies had to switch off gas and electricity indefinitely to prevent potential disasters. The hardest hit is the coastal neighborhood of Portuguese Bend, where residents are living on the edge. Literally. It always had amazing ocean views and cool sea breezes, with horses and peacocks still wandering the tree-lined streets. But now, it's like an earthquake hit. Only this time, the earth isn't stopping. For many, this place feels like paradise, if only the land would stop shifting beneath their feet. So the locals don't give up. Some of them had to leave, but many are determined to stay and fight, despite the destruction. But they still have to pour in hundreds of thousands of dollars to save their properties. People have installed generators to keep the lights on and set up sewer systems and pumps to drain the groundwater causing the landslides. Some say that the only way for these neighborhoods to survive might be to go completely off-grid, installing power walls to store energy and stuff like that. People are trying their best to run the sewer system off generators. They hope that they could get rid of this water in the soil that's causing these hellish landslides in the first place. They're determined to fight, but they will need help and support from the government to fight this disaster. Landslides are actually more common across the US than many might think. And new maps and data show that tons of people in the country might be in danger. Scientists managed to create the first very detailed, very cool map that shows where these landslides might happen, county by county. It's based on a lot of data and the history of 1 million previous landslides. They say that nearly 40% of the United States is at risk of experiencing landslide activity, which could lead to some insane catastrophes in certain areas. Luckily, now both residents and engineers can keep this in mind. But all this shows how vulnerable we are to natural disasters and how we should always stay alerted.